All right. Hey, everybody. Thanks for dialing in. Appreciate you. Glad some folks are here. So I've got some stuff ready for today, and then assignment one will go out later this afternoon. Let me see. So the main thing is we're actually a little bit ahead, which is great. It means we can do more cool stuff and do some more stuff in a little bit more detail. So mostly what I'm going to do today is wrap up our discussion about color spaces and run through some Python notebooks that are they're on my Git repo. I do a much better job of keeping that up to date than making lots of little changes to what's already on my courses. So if you're interested in getting a hold of these, you can just come grab them off of Git because, like I said, I'll update that, but I will almost certainly not update stuff in my courses every time it changes. So with that, let me share my screen. First, all right. So the first thing, actually, wait a second. Let me make sure I've got the chat pulled up in case somebody drops a message and I miss it. Okay. Here we go. All right. So, like I said, we're going to do some demos today and some notebooks. The first thing I want to do is kind of walk back through this real quick. The idea is that we have sort of established that a digital image is an array full of other arrays. And each entry inside of the digital image is a pixel, and the pixel can be pretty much any arbitrary thing we want. It doesn't have to be RGB or HSV or HSL or anything. We can pretty much put whatever numbers in there we want. But the format of the image is sort of determined by what is in the pixels, or rather, the way we've tried to frame it is the image is a coordinate system, and a pixel is essentially a point within that coordinate system. So an image is an array, and the format of the image is determined by the coordinate system of the pixels. And because we treat them like coordinate systems, there's all sorts of transforms we can do and transformations, and where all the linear algebra heavy lifting comes in CV. It comes from converting between coordinate systems, and we'll spend most, if not all, our time looking at color spaces. So, images that are some variation of color that we can display on the screen and look at and do computer vision with. So that was kind of the goal. And we talked about how, we changed them. There's kind of the big three that we work with, which was hue, saturation, value, hue, saturation, lightness, and hue, saturation, intensity. Said, value is the maximum color, maximum intentness inside of maximum intensity, sorry. It's basically whichever color is the most is what becomes the hue for hue, saturation, value, and that's value is just the brightest. Hue is where we're normalizing and putting it on this color wheel. V is the max of all the colors. So we looked at this, sort of cylinder where hue is the color, saturation is how much of that color there is, and value is how intense that color is within the pixel. So then we talk about hue, saturation, lightness, which is, in this case, we're normalizing it. We're looking at some different max values and essentially looking at, kind of a measure in the change between the min and the max. So how much light is there sort of across the pixels and across the min and the max. So, hue value is just the brightest color. Lightness is the sort of average of all the colors. And in this case, again, hue is our color around the color wheel. Saturation is how much of that color we have. And now we're just looking at lightness, which is essentially how bright or how close to the color white each pixel is once we found the hue. So the difference between them is, right, I said value is like we're projecting a color onto black. So max value would be black. Lightness is like projecting the color onto white. So max value would just be white. And, we kind of talked about HSI and HSL are much better for humans working with images. So those kind of fit in with the way our eyeballs work best, which is we're good at, as people, at seeing, a color and then, sort of what the color is on a continuous spectrum, light yellow, sort of light yellow, kind of yellow, pea green, green, grass green, whatever, we have a lot of really fun ways of talking about hue, I suppose. But that's what we see as people, is we see what color is it and how bright is it and how light or dark a version of that color is it. And that's why you see HSV and HSL in most photo manipulating tools and most sort of computer graphics tools in general. And, we pulled some of that up and we'll go over some demos in a minute. Just, once we're kind of done reviewing these, we'll start with the demos. But HSL, like I said, that's the color space you're going to use the most if you're editing things by hand or if you're working in like Paint, PowerPoint, basically any graphical software. If you want to monkey around with the colors, you're going to be doing it in HSL. Unless you're doing one of the other color spaces because you know a lot about what you're doing and how you want to solve your problems. Yeah, so the last one we talked about was HSI, which is hue saturation intensity. So the difference is, right, we said, for value, it's just which one's the brightest. For lightness, it's the combination of the brightest and darkest to measure kind of the total overall intensity. And then intensity, just HSI, is the average. So it's sort of, with value, we care about the brightest pixel color. With lightness, we care about how much more of that color there is, right? What's the relative brightness to the other two colors? And intensity is we're collapsing into one value where we just care about the total energy in that pixel, or the total light, which is just, adding up our RGB energy band numbers and taking an average and finding out, what is the total intensity inside each pixel, regardless of, how much of what kind of color is there. And so kind of we wrapped up by thinking that, kind of talking through HSI is the biggest one we're going to use in class and in most computer vision, because whereas, value and lightness are great for a human to look at and interpret, right? People are really good at that. Intensity is what a computer is very good at looking at. So when we talk about computer vision, a lot of where we start from is with some form of transform into an HSI space. And even if you aren't going specifically into hue saturation intensity, there are a lot of color spaces that are very similar that work in the same way, because that's just how the computer likes to see it, right? So there's the color, how much the color, and how strong is that color. Or if I'm a machine, what I really care about is what is the strongest color relative to all of the other colors in this pixel, and what is the total energy in this pixel as it relates to the pixels around it. And that's why we kind of said HSI is where we start for edge detection and image segmentation, because the intensity changes a lot whenever the thing in the image changes. And so a small change in color between, say a line and a circle next to it, that's kind of a bad example. But if you think of, if you look at your monitor, you've got your box that's your Discord or whatever open, and then there's a line around that, kind of, and then behind that is going to be your wallpaper or whatever it is. HS, let me see. Yeah, value and lightness don't necessarily change a lot when you go from one color, one hue and saturation to another, whereas intensity will, which means if there's a change kind of in what is inside the image, if there's a different object or a line or a horizon or something like that, you're going to find it easiest using an intensity value because you're looking for change, and intensity changes the most as you sort of slide around all these different color spaces. And we kind of wrapped up with this one color solid that sums up, everything we've been talking about in terms of the color spaces. So like I said, we're kind of wrapping up color spaces today, and then we'll be moving on to edge detection and filtering come Thursday. But the idea is within a color space, what we care about is what is the color of the pixel within some sort of color space? What is the saturation of that color? So how much of that color is in that pixel? And then we either want to know, how bright is that one color? How relatively bright is that one color as compared to every color inside of the pixel? And how objectively bright is that color? So those are our three measures. Those are our three color spaces we're going to work in. And that's kind of most of assignment one is going to look at moving between color spaces and, kind of looking at how you can make arbitrary transforms that, like I've said several times, as long as they, a couple simple rules, the only sort of hard, fast rule being it has to be some sort of discrete value. And assuming you start from there, you can kind of do whatever. So that was the goal. And like I said, kind of the goal of looking at it from a coordinate transform color space point is to, help you guys understand you can come up with any sort of custom image space. If you think it will help in your project, or if you think, you have a good handle on how color spaces work in general, you can kind of do custom ones where, if you're doing road segmentation, you can go in and fine tune it and say, hey, only, look for these changes or within this color space. And, I can do my own conversion to make the roads look brighter or dimmer, depending on my application or my knowledge. So that's the general idea on color spaces, and we briefly touched on some of this stuff, but so we're going to go through some demos now, right? So what we talked about last time is you're going to use a hue saturation value or a hue saturation lightness. That is what color selectors work off of. And so if you're just in Paint, I can come to my little edit colors thing, and I have the option of entering pixel values, right? So yeah, So this kind of puts me right here at this blue, and then over here, I can mess with my saturation and lightness with kind of this slider over here. So I have the option of working with the RGB values if I want to select a color to use, but that's really cumbersome and I can't really look at it as it's happening. But what I can do is just kind of move through here and choose a hue I want and set, my saturation and lightness over here, and I've got a color. Because this is, like I said, this is what humans want to see, is they want to look at something and say, I want this color and I want this much of this color, right? So that's kind of how it works in something like paint. The other thing is, I've got GIMP pulled up here. So if anyone actually has never used GIMP and cares and is interested in more hands-on stuff, I can dump some info about GIMP on the My Courses if people are interested. Like I said, I haven't really done like photo manipulation with it, right? I do a lot of, if I'm doing publishing or I'm writing something and I need to convert an image format, or I need to change a little bit about how the image looks or cropping brightness or whatever, I'll use GIMP. But other than that, right, I don't use it as a Photoshop surrogate. But that is kind of its goal in life, is to be, open source Photoshop in the same way you've got, right, Open Office and Libre. That really wish they were Microsoft Office, but they're open source and they're good. So anyway, if there's any interest, just let me know. But what I wanted to show with this is I've got a hue chroma lightness value and a hue saturation lightness value. And I can look at both of these. And the goal is, when we look at this, we talk about how the hue and the saturation are really important to people. They're not particularly important to a machine or a computer vision machine. And that's because computer vision cares about changes in the image. And so you can kind of see, if I move the color around, right, if I kind of change the overall hue, not a ton changes, nothing from, say, a CV algorithm's perspective changes, because we're just kind of keeping everything the same. It's now just a little bit of a different color, right? And with hue, you can kind of see we've got some changes here at the very extreme, where it finally starts to kind of pick out some stuff that's different. And then lightnesses are, we're projecting it either onto white or onto black. So this is just kind of, how light everything is. So you can see, hue doesn't change a ton. The chroma, color kind of changes the most here. And then lightness, you can see kind of at the very edge, you get some more stuff depending on what your chroma is set to. So anyway, the other one is hue saturation. So if I change the saturation way up, not a lot changes. If I mess around with the lightness, and the thing is with GIMP, kind of one of the things about why it's not as good as Photoshop, or one of kind of the finicky things with it, is hue chroma is an HSV space. Hue saturation is an HSI space. So saturation on this slider is not the same as saturation on this slider, which is really annoying. And it's one of the things you kind of have to be aware of if you're working in open source software, I guess. But the point is, you can see when I change lightness, which in this case is intensity. I think I said saturation. Lightness means intensity on this one. So this is actually HSI. It's just labeled lightness because I'm sure there was some dumb convention at some point. But the point is, this is what changes it the most, right? This is by messing with the intensity. That's when all of these little changes start to pop out. If I am here, then I see one kind of thing. But if I blow up all the way over here, some features come out. Or if I want to go all the way down here to the other side of the spectrum, some more features pop out. So that is just kind of which window is that? Okay. Yeah. So that's just a really quick demo. You can see when you pull up, Paint or GIMP. Right. If it's built for people, it's going to care about some measure of lightness of value. If it's built for a machine, it's going to care way more about intensity. So we can kind of see that in these programs, and we can kind of see how those are used and a little bit more about, kind of the utility of color spaces. So with that, I wanted to go through some of the notebooks that are available on the kit. So we went through this one a little bit last time, where what we want to do is just look at kind of the basics of seeing an image and displaying an image. So, we started out with our RIT logo. We're like, okay, well, I ran into OpenCV and it's blue, so then we're kind of like, oh, okay, well, I gotta, fix the BGR to RGB so that red and blue are swapped, or red and green are swapped. Then, I can load it in here, and I try to convert it to gray just using the image structure within Pello. I didn't get great results. And so I kind of tried a different way, and I still didn't get great results. And I kind of tried it again, and it still wasn't really working. We kind of figured out, well, the best way to do it is to just, load it in grayscale. And that way it, saves you some time and saves you some runtime if you're going to immediately convert it to grayscale, like you do with edge detection, like you do with some other stuff. And this is just a conversion that didn't work last time. I wanted to show this time, so it's another one we're going to pull from for segmentation and filtering, which is we can convert it to just a binary image, right? We can give it some sort of threshold and say every pixel whose intensity is above this threshold is black. Every pixel whose intensity is below that threshold is white. So we create this binary black and white image. And this is also really useful because you can see in this version, right, it's way easier to see lines. So if we were doing line detection or edge detection, all of those are much clearer now versus, any of these versions. But you're going to get a lot of problems if you don't make some other choices. So there's a lot of stuff that kind of goes into deciding ultimately. This is just a conversion that heightens the colors. And here was our YUV we talked about. And in this case, it didn't work out because we didn't fix the size of the image. So we got a bunch of repetitive garbage padded on at the end. We'll come back to this binary image. The problem you get if you do edge detection on this is, depending on where your threshold is set, everything inside the face that looks like a little tiny line is going to get flagged as an edge or a line. So in some ways, we can do this conversion and say, okay, well, it looks easier to do this type of computer vision, but that won't always necessarily be the case. There's a lot going on inside of the image and the color spaces and the way they're transformed that you need to be aware of to work with images and do cool stuff with CV. So that was kind of our first notebook. And then the next thing we wanted to do was look at the HSV color space. So, we'll start the same way. We're going to load in our image, and now we want to do some computer vision with Godzilla, King of the Monsters. So what we want is now we have our Godzilla image, and we talked last time about how OpenCV has a jillion million conversions in it you can just use. So the first thing we can do to get to an HSV space is we just ask OpenCV to do it. And this is what we're left with after we convert. And what you can see after this conversion is you can tell where all of the shadows are, right? All the places on our original Godzilla that are way darker, that are sort of shadowed by the lighting. So you've got kind of the shadow in the armpit and his neck's shadowed, and a little bit under the elbow of the next arm, right? If we look at this, it's kind of hard to say if there are any shadows, right? But if we move to an HSV space, now it's very apparent where those darker areas are that represent the shadows. And what's cool about that, this is way off topic, but with looking at shadows and detecting them, it's fun to kind of try and figure out where the light source is, right, relative to where the picture was taken. So if you see the shadows, you can make some really good guesses as to where the sun was when this was taken, if assuming it was taken outside. Also totally unrelated to anything, but the original Godzilla costumes were made out of cement and weighed several hundred pounds. So they could only film for like 30 seconds at a time because there was no rubber in post-war Japan. All right. Anyway, that's your fact about Godzilla for the day. The next thing we want to look at is, we know that's a coordinate transform, and we know all the formulas to accomplish said coordinate transform. So then the idea becomes, can we do this manually through just doing the math? So what I've got here is all the formulas for an HSV transform. And if we run through it, and if we look at it, we get a bunch of errors that I said I would be really mad if your code had, but I get a pass because I threw this together for a demo. And I'm in charge, so yeah, that's what we're doing. But our hand-drawn, right, the one we did on our own for HSV, doesn't really look like this, right? But it also doesn't really look that far off. We can still see the areas that are shadowed. There's some weird jumps around the shadow in the armpit with all these little white squares. And that's because we need to move to RGB if we're going to be doing translations in the RGB space. So that's again, right, every little step or every little kind of color transform can give you some problems. Don't actually think I fixed the code of that plug, speaking of. Right, yeah, so this is just to show if the code doesn't work. So what you can see now is if we add in changing to the RGB space, then running through our calculation because all the formulas are in the RGB space because that's what people think of them and work on them, and that's how monitors display them. So even if we want to do the transform ourselves and we know the equations, we still have to know from which color space we are coming and to which color space we are going. So if there are any little conversions like that we have to make, we know, and we're not, caught off guard because, depending on the application, it's not hard to see kind of our not great transform and still kind of accomplish what we want. What would happen, or what people have done, and I say these things because it's things I've done when I started in CV with, no background in computer vision whatsoever, right? Is you'll come across a problem like this where it's easier to just write a second filter to remove all the white pixels, right? And you can just be like, well, I just, make them the average color of the whole thing, or just totally remove them, blah, blah, blah. You come at it, and without understanding sort of the fundamentals of the coordinate systems, you won't be able to fix this, right? You won't know what went wrong. The assumption would be, okay, well, just when I move to HSV, some garbage shows up, whatever. I'm going to get on with my life writing algorithms to detect Godzilla. And the other thing to notice is here is sort of the correct version. Here's the version we botched by not changing from BGR to RGB. The other point of kind of, if you just find a way to throw out all the white boxes, this would still work, right? This is still a workable image for a computer vision application, which just also is kind of there to highlight how in an HSV, HSL, or HSI transform, the values of the color, right, the actual color of the image does not matter nearly as much in these types of transforms, because what you're really trying to get at is big jumps in lightness, intensity, value, brightness. Whichever one you're looking at, you want to see where that changes a lot. And so, if I mix up my red and my blue, or my red and my green, or red and blue, I can still come very close to the right solution, because everything is sort of either an absolute intensity or an intensity relative to the other colors. So it still kind of works out to what we needed it to be, even though, we kind of botched the conversion. And if I come in here and I fix it, now that I've got the right conversion, because I put it in the right coordinates, I have a better version that I can work with a lot easier. And that just, goes to show, if you got to know what you're doing to do it well. They are not because of the type error, or that's what I've got here. No, they're an actual artifact of how this kind of gets botched by not changing from red to green to blue. So it's a little different here because that was the problem right here. In this version, all the stuff below there is because, we messed up our coordinate space size and had a bunch of garbage kind of thrown at the end. Here, all the garbage shows up just by way of us doing the transform wrong. So that was HSV, right? That was this idea of, okay, we want to go between RGB and HSV and value and see, all good, you're welcome. See kind of how that works, right, and why it works. So the next one we're going to do is look at HSL and HSI. So if I pull my stuff in and I just kind of cut out the middleman entirely, read the image in and keep it BGR, don't even bother with that, just throw my CV2 transform at it. And this is where we get, our Terminator smashing its skull as it walks across the field of bones. Um, as all my pop culture references are about 40 years old, so hopefully it tracks for someone. But this is what we get when we go to hue, saturation, lightness. And if we want to look at, actually, this should be, okay. So what we have now is our hue saturation value. So you can kind of see here with lightness, I'm kind of measuring the relative intensity of each color. So, the foot kind of pops out, and the tops of some of the skulls that are really well lit pop out. With HSV, it's really hard to see anything in that, both for a person and a computer. So you can kind of see in the hue saturation value, we're not getting any new information. We're not seeing anything we can work with, and neither is the machine, right? Whereas with an RGB to HSL, now we're getting a little bit, more information that we want, that we can work with, and some features are popping out a little bit, a little better, a little warmer. So let's look at, right, if we can convert to hue saturation intensity, because this is the one, this is the one we want. This is the one we're probably going to work with the most. This is kind of the biggie. And for whatever reason, OpenCV cannot do it. There is no color to HSI transform inherent to OpenCV. I'm not entirely sure why, other than the fact that somebody figured out they could make money if they had it and OpenCV didn't. So there's a guy or some entity out there you can give money and they will give you access to a color to HSI conversion. But in general, if it's something we want to do, it's something we're going to have to do on our own. And, this is kind of where knowing how everything works really comes in handy, because, if you kind of run up against this wall of, well, I can't get to HSI from color image, and the only way to do it is to basically do the coordinate transform by hand, right? Actually go in and by manipulating each pixel and translating each pixel from RGB to HSI, you can get to an HSI image. We just have to do the work ourselves. So let this run. And I made my own way to see an HSI image. And you can see here, it's got some features are standing out more than before. You can kind of see the backs of the legs are very, very, purple, whereas everything else is, got this green color. So you can see some more features in this image than you couldn't see in the other images. And it's kind of ultimately our job as the people doing computer vision, if, we plot everything side by side by side. Sorry, that's so small. right? You can see in each case, by converting between these coordinate systems, I am making some features stronger, some features lighter or harder to see. And I kind of need to understand each space and what, especially, value, lightness, and intensity all mean, and that will inform the very first step of whatever CV task I have at hand, which is going to be some sort of, process this image. It's a color image, and however you process it, you kind of need to be able to think back to what color space is it going to be easiest to process it. The answer is usually HSI, but that's kind of the ultimate goal, is to know enough about the background of digital images and how they are constructed to make much better initial guesses at what coordinate space you want to work in, and if you want to translate to some form of hue saturation in terms of your coordinate space for your image. So that was kind of the demos I had. Like I said, I'm going to dump all this on the Git repo just because it changes too often and too fast to try and put it on my courses. The other thing I wanted to look at for kind of giving this demo is, so this code to manually change to our HSI plot, which we get here, we can, look in, we can do the math, we can, kind of figure all this out on our own. But in this instance, I also just asked ChatGPT to do it. So this is the kind of thing generative AI can do, right? This is something, it's a function, it's got some math in it, it does some linear algebra kind of stuff, it monkeys around with some arrays, and this is all stuff we can write, right? We're all, smart enough, we've got this far in life, we could very easily code something like this, but this is also the kind of thing generative AI can code well. It's very, very good at a simple function, right? If you kind of look down and you see the code, it's got, some imports, and then it defines this function for me that returns an HSI image by, doing all of the math stuff for us. So this is, I like to show this because I would like everyone, to kind of leave, if not college overall, certainly at least from this course, with some understanding of kind of the limitations of generative AI for coding, and what you can do with it and what you can't do with it. And what you can do with it is it's very easy to ask for a simple math problem like this, or a function to do some matrix multiplication. That's, easy peasy. It takes 5 minutes to do something that would have taken more like 50 if you did it all by hand. What ChatGPT or any other generative AI cannot tell you and will not be able to tell you is which color space you want to be in for which application. So you can't, you can ask, hey, what are applications of HSI in computer vision? And it can give you some stuff, but you can't really show it an image or a set of images and say, I need to, segment a desk out of a picture of a classroom. And I need, so I need, here's a set of pictures. You go do the transform, you do the filtering and the edge detection, bring all that back to me. It can't do that. And it's not going to be very good at it. And it's not going to have any sort of concept of what color space you would want to use, or how to step through color spaces if you want to use different ones across your across your project or across your application, whatever it is you're doing. So, and the main thing about generative AI for coding, besides the fact that it's not very good, so you don't need to be as worried as I know a lot of people are. But the other thing is, it can't stitch together complicated tasks. So I can ask it for this function that will change the HSI. If I then ask it to add on to this function, okay, well, I also want to be able to go from HSI to HSV without having to step back through the RGB color space. Can I go straight from one hue saturation space to another? It's not really going to understand that. It's not going to be able to help you with that. And by the time you get about 3 requests deep, it's kind of just gone insane. Because it's very, very bad at sequential reasoning. And all generative AI is very, very bad at sequential reasoning because it's ultimately just an extremely talented and complex autocomplete. All ChatGPT is doing is predicting what the next word it should say is based off of the word in front of it. So it can't really work through a complicated problem, especially since when it turns on, when you start your first session, it essentially has zero memory, right? It doesn't know what you were talking about. It doesn't really keep anything in the cache. So, it's not going to be able to kind of reason over time the same way a person can. So, yeah, that's kind of, my initial example of, what you can use generative AI for, what you can. And when I send out the, let me see, I forgot my words. Oh, the assignment 1 comes out later today. There'll be questions you can probably solve with AI, with ChatGPT. And if you use it, that is fine. I use it for the lecture notes, so I can't really say you can't use it for the project. But like I said in the syllabus, what matters the most is that you tell me which one you used. I haven't seen anyone use something other than ChatGPT. I think just because ChatGPT has really good branding at this point, it's what everyone thinks. And this is another aside, but as I've been applying for jobs, every AI job is basically, we're going to make a large language model better than ChatGPT. That's what the job postings say, literally. And it's one of those things where if you're already having to say you're better than something else, you've kind of already lost. Like, you're admitting from the jump that ChatGPT is better or best, and now you're trying to be better than, ChatGPT. It'd be sort of like if, Sam's Cola said they were going to make the next Coca-Cola that was even better than regular Coke, because the implications, it's already inherently better, so we have to try to be at least as good and then try to get better. So, yeah, I guess all that to say, ChatGPT has really good branding and market visibility, and there's really only so much data left to train on. There's a tremendous amount of freelance work to be done teaching these things how to write code. It's not working, and it probably will never work particularly well. There's still quite a lot of thought and creativity that goes into writing elegant code. But anyway, ChatGPT is not going to replace anyone anytime soon, because we're approaching a ceiling where there either need to be thousands more people with computer science degrees teaching how to do computer vision, or more data to suddenly appear, but we're kind of out. And at this point, data poisoning is becoming a serious issue because it's sort of a snake eating its own tail, because there is so much artificially generated content. There is no learning off of artificially generated content. So it's not actually learning how to perform a task, it's learning how to perform a task the way AI has already done it, right? So it's just sort of training itself on itself, so there's no possibility for improvement. Um, anyway, that's thank you for coming to my TED Talk. I don't like generative AI, and I don't really like working in that space, and it's been finding a job for it, but it's all worth it, I guess. I don't know. Anyway, I don't like generative AI, but it's really great at stuff like this, is sort of the thesis of my argument. Really awesome at short functions, really terrible at writing code, abysmal at best at writing any sort of optimized code or making any sort of informed decisions on what code you need to run or how you need to approach a problem. Uh, so, like I said, anyway, thanks for coming to my TED Talk on generative AI. All right, we've got a little bit of time. So we'll wrap up a little bit early, but I do want to go ahead and introduce kind of the idea of edge detection and image segmentation. So actually, no, we need to go through filters first. This is on my second. Okay, yeah, I'm just going to run through a couple kind of key points real quick that we're going to discuss. Uh, oh, that's because I was singing a song to myself about looking for files, and I don't think anyone wanted to hear me narrate my life through the medium of song. All right, so let me share this again. So this is what we've been talking about for like 2 weeks. We've kind of beat this topic into the ground 10 times over, but it's kind of the most important thing I need to know to go forward any further is, how we treat it as a coordinate space and how changing coordinates lets us do computer vision. This is a solid. So what we're going to talk about next is going to be filters and edge detection. And, based off of kind of some of the stuff the other class does and the way the book does some stuff, we're just going to talk about edge detectors and filters at the same time. Like I said, some people kind of lump edge detection into 2D filters for images because you're filtering out the edges essentially, or filtering in. I don't know. You want to get rid of everything that isn't an edge. So it is a kind of filter, but it's also kind of its own thing. So we're going to talk about filters and then we're going to talk about edge detectors. So we're going to talk about, filtering first and how we get to a place to do edge detection. But to kind of set the stage for why we do edge detection and why it is kind of, next to color space transforms or coordinate space transforms, it's, finding images is kind of the next most important thing for CV, and it's sort of the next foundational step that we have to, wrap our heads around before we can do any new stuff. Uh, and so, kind of to set the stage, like I said, as a person, if I'm going to walk through a classroom and find a place to sit down and sit, right? Well, if I want to do that, I don't really need to know the color of the desks. I can, segment a desk out from the rest of the image. I don't really need to know the color of the chairs. A chair is a chair. I don't need to worry about what the desk is made of. I don't really need to worry about what's on the floor, right? To get from the door to a desk to sit down, uh, all you really need to know is where the desk is and where the chair is in relation to everything else around it, which means you really only need to know the edges. If you have the outline of a chair and a desk, then you can find your way to that chair and desk and sit down. So, what that means is image classification and segmentation start with geometry. The first thing we want to do to process an image most of the time is to segment it into different areas. And so, kind of our first step is geometry based, where the shape of things and the relative shape of things is what I care about the most when I first start. I don't look at the color of every pixel in an image if I'm looking for a soccer ball, because there'll be lots of pixels the same color as a soccer ball. The first thing I look for if I'm looking for a soccer ball is going to be a circle, right? And so that's what we're going to do going forward. We're going to kind of learn about, right, this idea that if we do edge detection, what we're trying to get at is before we do anything else, and again, most of the time, the first thing we need to do is work with the geometry of the image. So that's kind of, the first step, and why we're going to talk about it, and why it's seen as a filter, because I'm essentially filtering for what I want in the image. But, if I do edge detection on my classroom, I can find where a desk is and I can find where a chair is, and I can walk in there and sit down. A lot of the information that isn't just geometric does not matter to me yet in this kind of task. Uh, so yeah, that's what we're going to be talking about going forward, is filtering and edge detection. And that'll kind of lead into segmentation, to where we can figure out how to best filter an image, best detect edges in it, and then kind of move forward with our CV task. And the other thing, oh yeah, so this is also why we look at the HSI space so much, that I've kind of been talking about. As you can see, the color between the tops of the desks on the floor isn't that big of a difference. They're both kind of a off-white. One's bright white, one's more of a cream. The wall is also bright white. So if I start from a place of caring about hue or saturation, um, the desks will look like the wall, will look like the floor. There's not very much variation in the hue saturation space in an image like this. Whereas if you pick out intensity, the intensity, wherever it goes from one surface or one color to another, even if it's only a very small change, still kind of pops out in an intensity space. So this is why we get to HSI. This is why we use HSI for edge detection. And next time we're going to start talking about how we do edge detection and how we do image segmentation from there. So I'm going to wrap up there for today. Um, are there any questions, comments? Anyone need anything? Getting through the material pretty quick, which is nice. So I'm gonna take it everyone's good. Awesome. Thanks for
Professor, I
joining.
actually had a
Have a
question.
great Tuesday. I'll see y'all Thursday. Bye.
Professor, I had a question.